Hello everyone. In this chapter we're going to talk about the data link and network layer protocols in TCP/IP. This corresponds to chapter 4 in your book. In this chapter we're going to explain the fundamental concepts associated with the data link layer protocols that operate over different network link types. We're going to distinguish among the different types of packets used on IP networks. We're going to describe how hardware address resolution occurs for both IPv4 and IPv6 with Address Resolution Protocol, or ARP, and Neighbor Discovery Protocol, NDP. We're going to explain the essentials of the Internet Protocol both for IPv4 and IPv6. And we're going to include route resolution processes, IP datagrams, fragmentation, and the differences between IPv4 and IPv6. We're going to talk about the mechanics of IP routing, how entries are placed in a routing table, and how the basics of routing operate on an internetwork. And we're going to describe the intricacies of IPv4 and IPv6 routing characteristics, including the methods of preventing routing loops, general behaviors of routers, and routing determination. We're going to talk about detailed information on IPv4 and IPv6 routing protocols, including the structure of routing packets and the behavior of each routing protocol. We're going to describe the various factors involved in choosing how to route between different network environments and infrastructures. We're going to talk about the fundamentals of routing to and from the internet. We're going to talk about the basics of securing routers. And we're going to describe the tools used to troubleshoot IP routing. So, in data link protocols, the key functions of the data link layer, we talk about MAC, or Media Access Control, and the Logical Link Control, or LLC, as well as point-to-point data transfer. So we're shipping data from one MAC layer address to another. So WAN encapsulation of frames of the data link layer, it involves one or more of the following services. We have addressing, bit level integrity checks, delimitation, and protocol identification. And then also, remember the OSI model. So where the data link layer is located, so this operates on layer 2. And the data link layer operates for both LANs and WANs. Also note the 802.2 standard, that's with IEEE. It describes the function of the data link layer. What's interesting here is the standard also provides services for a bunch of other projects. So 802.3, or Ethernet, 802.5, which is Token Ring, MANs, or Metropolitan Area Networks, for 802.6, demand priority standards, 802.12, and 802.14, which are your cable modem standards. Also, data encapsulation techniques are used to enclose packet payloads for transmission across WAN links, and they differ from those used for LAN connections and involve specialized protocols and methods that operate at the data link layer. So we're talking point-to-point protocol, high-level data link control, synchronous data link control, X25, so frame relay, asynchronous transfer mode, or ATM. Also, when you think of the different standards, so T1 and T3, and E1 and E3, so T1 and T3 are prevalent in the United States, E1 and E3 are prevalent in Europe. They have slightly different speeds. So a T1 line has a data transfer rate of 1.544 megabits per second, whereas the equivalent E1 in Europe is actually 2.048 megabits per second. A T3 is a bit higher at 44.736 megabits per second, and an E3 is 34.368 megabits per second. Point-to-point protocol, or PPP, is a popular and widely used protocol as it provides frame delimitation, protocol identification, and bit-level integrity check services. RFC 1661 describes PPP, and you might consider looking it up as a reference. RFC 1661 includes encapsulation methods, the Link Control Protocol, or LCP, and a collection of negotiation protocols. Integrated Services Digital Network, or ISDN, and Synchronous Optical Network, or SONET, are both referenced here. You may consider looking those up as well, because as you progress on through learning about PPP, you're going to notice there's a wide variety of WAN protocols and technologies that we're going to mention. We could have lessons on each individual one. They're extremely detailed. But keep in mind, we're focusing on the data link layer here as a whole. So I'd say it's worthwhile outside of the course to pursue these. But here we just really want to understand this specific protocol layer. Important fields in the PPP header and trailer are the flag, the protocol identifier, and the frame check sequence. And PPP supports a default MTU of 1500 bytes, so it's ideal for interconnecting Ethernet-based networks or peers. At the data link layer, protocol data units, or PDUs, are called frames. A frame represents the same data that appears in digital form at the network layer in an IP datagram, in the form of whatever sequence of electrical signals mapped to that data. So the information from an IP datagram can be encapsulated in a variety of frame types. Here we're going to examine the TCP/IP communications on some types of local area networks. So here are some Ethernet frame types. So Ethernet 2 frame type. It's a de facto standard frame type used for IP datagram transmission over Ethernet networks. And it has a protocol identification field, or a type field. Ethernet frame types that TCP/IP can use are Ethernet 2 or Ethernet 802.2 for logical link control. It's tempting to think of Ethernet as a single frame type, since Ethernet 2 is the standard for Ethernet networks, much the same way that TCP/IP is the de facto protocol for LAN and WAN. But there's other frame types, and you need to be aware of them. Considering them unimportant might be a mistake in your learning. And a topic of Ethernet frames is where IEEE 802.2 and .3 come enormously and hugely important. You need to become extremely familiar with these standards to understand the structure and the functioning of Ethernet frames and how they work on a network. So in the Ethernet 2 frame structure, we look at the type fields. First is the preamble, followed by the destination address field, the source address field, the type field, the data field, and the FCS field. In Windows 2000 and above, the systems are typically configured to auto-detect the Ethernet frame type on the network. And again, Ethernet 2 is the most frequently used frame encountered, and Windows can be explicitly configured to use this frame type. Here's another view and a graphic of the Ethernet 2 frame structure. And here are the various assigned protocol types. Now the Ethernet 802.2 LLC frame structure, it's similar to the Ethernet 2 frame structure, but here it uses an SAP field instead of a type field to identify the protocol it's using on the frame. And here is a graphical diagram of that frame structure. Now we're going to talk about hardware addresses in the IP environment. Recall that switches and bridges operate at this level and freely pass ARP, So Address Resolution Protocol and Reverse ARP, or Reverse Address Resolution Protocol, broadcasts while routers block them. Since layer 2 addresses are not routable, when a node sends a message to a different device on a different subnet, the originating data link layer address of the packet is stripped off in the router. The router then adds the data link address of the interface that the router sends the packet out of and transmits it. When the frame is received, it reads the originating IP as the original sender, but it reads the data link address as of that router. So again, IP addresses, they individually identify IP hosts on a TCP/IP network, and a hardware address is required to get the packet from one IP host to another IP host on a single network. So ARP and NDP, so again, Address Resolution Protocol and Network Discovery Protocol. The Address Resolution Protocol, or ARP, is the protocol that's used by IPv4 nodes to resolve at the network layer, or IP, addresses into data link layer, or physical addresses. IPv6 doesn't use ARP, but instead uses Neighbor Discovery Protocol, or NDP. NDP is similar to ARP in that the IPv6 node that wants to know another node's physical address sends a neighbor solicitation request, and the desired node replies with a neighbor advertisement containing its data link layer address. The ARP cache, so when we're talking about ARP protocol characteristics and handling, the ARP cache is a table containing hardware addresses that's learned through the ARP process. This diagram highlights some of the characteristics and the handling of the ARP protocol. And here's a diagram of the ARP frame structure. So when we think of ARP packets, fields, and functions, basic ARP packets broadcast the ARP request packet, directed or unicast ARP reply packet, and the most confusing part of ARP is the interpretation of the sender and target address information. Think of an ARP request as a message from the sending PC to the receiving PC saying, "This is your IP address. What's your MAC address?" Think of an ARP reply as a message from the receiving PC back to the sending PC saying, "I am the PC address, blah, and my MAC address is this." Here is a capture of a ARP broadcast packet. Here is a capture of an ARP unicast packet. When we talk about the ARP packet fields, there's a number that you need to remember: the hardware type, the protocol type, the length of the hardware address, the length of the protocol address, the opcode, the sender's hardware address, the sender's protocol address, the target hardware and target protocol addresses. With the ARP cache, ARP information is kept in an ARP cache in memory on most operating systems. On Windows-based systems, you can use ARP-A to view the table contents, and you can have a utility to view the IP and the hardware addresses. You can make changes to the ARP cache in the Windows registry. Now, there's always the warning that making changes to the registry isn't for the faint of heart, as you could corrupt your Windows registry, lose data, etc., but this is something that you can do if you want to play with it at home on your Windows-based machine. So Proxy ARP is a method that allows IP hosts to use a simplified subnetting design. It enables a router to ARP in response to an IP host ARP broadcast. Most network configurations may never need to use a Proxy ARP. Here is an example of an ARP proxy network design. In reverse ARP, we use it to obtain an IP address for an associated data link address. So it's initially defined to enable diskless workstations to find their own IP addresses upon booting or startup. So you have the Bootstrap protocol, or BootP, and eventually Dynamic Host Control Protocol, DHCP, which replaced reversed ARP. If you think of an ARP request as, this is your IP address, what is your MAC address, then a reverse ARP request would be, this is your MAC address, now what's your IP address? So with the Network Discovery Protocol, when we talk about its characteristics and its handling, it's specified by RFC 4861, and it's the IPv6 counterpart to the IPv4 ARP. And it describes how nodes in the same network link determine the presence of other nodes, discover the link layer addresses of another node, find routers, and discover network paths to network neighbors. Here is a diagram of the format of the neighbor solicitation methods in NDP. So now we're going to talk about understanding the Internet Protocol. Now, this is the point in the chapter where we move from the data link layer of the OSI model to the network layer. So again, remember the distinction between these two layers, but also remember some of it might be a bit blurry. So we're going to talk about network layer communications, so end-to-end communications. The Internet Protocol, or IP, it's a network layer protocol used in the TCP/IP suite. The Internet Protocol version 4, or IPv4, which is widely implemented, and we're transitioning to IPv6. So sending IP datagrams. These are the requirements for building an IP datagram packet to transmit on the wire. IP addresses of the source and the destination, and the hardware address of the source and the next hop router. The IP host can use a manually entered destination IP address or domain name system, DNS, if you're familiar with it, to obtain a destination's IP address. An IP host can either use a manually entered destination IP address, as we've said. Now, if we jump here, this is how a data link header is stripped off and reapplied by IP routers when a packet is forwarded. So the route resolution process, this is the path of blind faith. You can use the default gateway, is commonly used in the networks. These gateways are used as the initial routing point for data exiting the local area network. So this enables the IP host to determine if the desired destination is local or remote. Is it a local or remote destination? Well, when you've determined the IP address, the IP host compares the network portion of the destination address to its own local network address. Now, if it's remote, which router do you go to? So there's various types of route table entries. There's the host route entry, the network route entry. The receiving gateway typically does one of the following. It either forwards the packet, it sends an ICMP reply, or it sends an ICMP reply indicating it's unclear where to send the packet. So this is where I want to take a little chance to talk about the main difference between IPv4 and v6 routing. Now remember, previously we talked about how the fact that IPv4 uses ARP and IPv6 uses NDP. Remember, IPv6 packets can't be fragmented. For IPv4, the source node has to determine if the destination node is local or if it has to be routed. For IPv6, the source node uses PMTU discovery. IPv6 uses multicasts rather than broadcasts. So the lifetime of an IP datagram. So with IP packets, they have a predefined lifetime indicating each packet's time to live, or TTL, or hop limit in terms of IPv6. 64 is the recommended started time to live value. 128 is default time to live in Windows 2000 through Windows 10, Windows Server 2003 through Windows Server 2012 R2. So in terms of fragmentation and reassembly, IP fragmentation allows a larger packet to be automatically fragmented by a router. Once it's fragmented, no reassembly occurs until the fragments get to its destination, and all fragments are given the same time to live. And you know what, let me give another example first before we continue. Let's go back to fragmentation. This is really at the heart of packet switching. Think of a series of trucks numbered 1 through 10 leaving a warehouse. And they leave the warehouse in their numerical order with a destination. Let's say they're going from LA to New York. Let's say there's some problems on the road and the trucks need to take a different route. Once they get back to where they're going, then they're put back in order from 1 to 10 and unloaded. So the destination can receive these things at different times, but eventually it's going to put all of them back in order once it receives all of them. So service delivery options. As the internet and TCP/IP take on a bit more responsibility for commerce, people are looking ways to improve performance. So recently, the differentiated services, or diffservs, and explicit congestion notification, ECN, have been suggested to improve some of the IP traffic flows. IP headers support 2 fields for defining packet priority and route priority. We have precedence and type of service. So when we talk about precedence, a router uses precedence to determine what packet to send when several packets are queued for transmission from a single output interface. Some applications can be configured to support a higher precedence and receive higher priority treatments. There's 8 levels of precedence. Level 0 is for routine traffic, no priority. Levels 1 through 5 are for prioritized traffic with higher value, so a higher priority. Precedence levels 6 and 7 are reserved for network and internetwork control packets. And then the type of service. It's used to select the routing path when you have multiple paths. So example of routing protocols, open shortest path first, or OSPF, or BGP, the Border Gateway Protocol. A router has to be configured to be able to use TOS or other methods of assigning precedence. And basically, differentiated services is a method of specifying and controlling network traffic by class. Differentiated services is a bit different from TOS. Sorry, I forgot to flip the slide. Or 802.1, because it's a little more complex in terms of rule statements. And then again, you can think about this as the difference between like riding first class and riding coach in an airplane. Again, you're going to have preferences as you send these packets, and we can make sure that we have a means differentiating this traffic. So now we jump to IP routing, and we're going to start our discussion by talking about the routing table. So the routing table is a database that lives in the memory of the router. Entries in this database are known as routes and consist of a network address, a next hop, which is routing jargon for the IP address of the next router and the path to the destination, various metrics, and vendor-specific information. A routing table is the compilation of information about all the networks the router can reach. On small networks, it might just be a few entries, but on large or enterprise networks, there's several hundred entries in the routing tables. The routing tables that support the internet are the largest of all. The tables of the internet's backbone contain over 600,000 entries. So here we have just an example of a routing table from a Cisco router. Now, how are entries placed in the routing table? So again, recall a routing table is just a database stored in the flash memory of a router, and even your personal computer keeps a small database of routes. If you open a command prompt and type route print and press enter, you can see the routing table on your computer. A route entry can be placed in a routing table in three basic ways, either through direct connection, manual configuration, or dynamically by using a routing protocol. So there's two types of protocols that cross an internetwork: routing protocols and routed protocols. Routing protocols are used to exchange routing information. Routing Information Protocol, or RIP, or RIP, or Open Shortest Path First, OSPF, are different routing protocols. Routed protocols are layer 3 protocols that are used to get packets through an internetwork. So when we talk about grouping routing protocols, there's two primary ways to group them, which help achieve routing efficiencies and minimize external needs for internal networking details. So the first grouping is an administrative one. When organizations begin to connect to the internet, they quickly realize that because of the designs and the philosophies of one company were incompatible with another, they need a way to extract this information. The solution was to create routing domains. They're autonomous systems, which we'll define later, but each organization can have complete control over its own routing domain, set it to appropriate security levels and policies without impacting any other organization. So the routing protocols used inside a routing domain are called interior gateway protocols, or IGPs, and the routing protocols used outside are exterior gateway protocols, or EGPs. The second group of routing protocols is through the method they use to communicate. There's two really flavors of routing protocols, distance vector and link state. One of the most difficult challenges in automating the routing process is preventing routing loops. The simplest way of give an example of a routing loop, it's when one router believes the best path is through a second router, and at the same time the second router thinks the first router is the best path. So that's an example where you have a loop issue between the routers. And again, we talked about the distance vector routing protocols. Here's an example. So here's routers on a distance vector network tracking the distances. So the number of hops between the routers. And again, routing loops. You have router A, you have router B. Router A thinks best path is through router B. Router B thinks best path is through router A, and it just goes round and round and round. There's avoidance schemes, so you can use the counting to infinity scheme or split horizon, and that's you can couple that with poison reverse. So when we talk link state routing protocols, they differ from distance vector in two ways. They don't route by rumor, and they don't periodically broadcast their entire tables. And here's an example of adjacent databases on a link state network. When designing or operating a routing hierarchy, it's important to understand the characteristics of the networks involved and how they are interconnected. It is also important to understand the requirements and limitations of the various routing protocols that may be in use on the Internetwork. Convergence is the process in which all routers on a network recalculate the optimal paths after a change in the network. A network is usually said to be converged when all the routers know a loop-free path to get to all other networks. Ideally, a network should be in a converged state in which all routers know the current networks available and their associated costs. In terms of IPv4 routing mechanisms, these help routers learn about paths to a destination. In split horizon, it's used to speed up the process of convergence and resolve the counting to infinity problem. With poison reverse, it's a technique for assigning costs to routes designed to prevent routing loops. Here is a diagram of split horizon in operation. Time to live ensures that packets cannot loop endlessly through a network, and it's defined in the network layer header. Time to live is basically a countdown. Every time a packet hops, the TTL value decreases by 1 until it either arrives at its destination or it reaches 0. If it reaches 0 before arriving at a destination, it's dropped. Now I want to jump back real quick, if I can. When we talk about split horizon, when you're using the split horizon rule, a router never advertises a path back out the same way the router learned about it. And then in terms of poison reverse, when one router learns about a route or a set of routes from another router, it assigns those routes in an infinite cost value, so they'll never end up advertising routes back to their sources. When we talk about ICMP router advertisements, some routers can be configured to send periodic ICMP advertising packets. These periodic advertisements do not mean that ICMP is a routing protocol. It just allows hosts to learn passively about available routes. In terms of unsolicited ICMP router advertisements, these are sent periodically to all hosts' multicast address of 224.0.0.1, and typically they include the IP address of the router that sent the ICMP router advertisement packet. So, black holes is a term you should remember, especially for the midterm and the final. The Border Gateway Protocol, or BGP, experiences black holes sometimes. Some causes are a deliberate attack, misconfiguration, or deliberate administrative decision to disable ICMP. So what's a black hole? It's when ICMP is turned off and a router discards packets without sending any notification about its actions. In some cases, you might disable ICMP because it's being used as a tool to explore a network for information in preparation for an attack. Here's a diagram of the process for dropping oversized packets. So areas, autonomous systems, and border routers. So OSPF utilizes what are called areas. They're groups of contiguous networks, and it reduces the number of entries in the link state database. According to the OSPF spec, it defines the need for a backbone area, area 0, and autonomous systems, ASs. They're groups of routers under a single administrative authority. So all other areas have to be connected directly to this area, but there's some allowance for special tunnel connections. And the routers that connect these areas are sometimes called area border routers, or ABRs. And ABRs can summarize routing information before sending link state packets to other networks. And here's an example of areas connected to a backbone, area 0. So some routing considerations in IPv6. Remember, IPv6 was designed with routing efficiency and throughput in mind. So it's designed to reduce the workload of internet routers. Now, many of the same routing approaches are familiar from what you've learned with IPv4, and we'll use these concepts to make the transition to IPv6. In terms of routing mechanisms in IPv6, routing mechanisms are processes by which a router learns about network paths that lead to destinations. Network nodes have to use PM2 discovery to determine an arbitrary route to its destination. And some of the dynamic routing protocols in IPv6 are RIPNG, EGI, RPv6, OSPF v3, ISIS for IPv6, BGP for IPv6. In terms of IPv6 routing table entry types, nodes and routers maintain their routing tables. And in the route determination process, a device should select as its forwarding decision. A router compares the bits in the address prefix for each entry in its routing table. A router then creates a list of all matching routes, and a router chooses the route with the largest prefix length. Here's an example of the IPv6 table fields. So in terms of strong and weak hosts, RFC 1122 is the original specification. And hosts use different behaviors to determine when and how unicast traffic is sent and received, and whether it has to be associated with the network interface on which the traffic is traversing. The IPv6 delivery process is end-to-end. So the source node sends a packet to either a router or to the final destination, and if the destination is the same on the local link. If it's sent to a router, the packet's forwarded to either another router or its final destination if the node on a link is directly attached to the first hop router. And when it's received by the destination node, the packet transfers its data to the desired application on the computer. Multicast listener discovery in IPv6. So when we look at MLD and MLD-v2, MLD enables each IPv6 router to discover nodes that want to receive multicast messages. MLD-v2 updates the protocol and supports source filtering. So in terms of IPv6 multicast behaviors, multicast is a method of sending a one-to-many message in real time, usually using ICMP v6 as the transport mechanism. And here's a logical diagram of the multicast message being sent to a multicast group. Here's an example of the MLD v1 packet structure. And then some changes in MLD v2's packet structure for the multicast listener query message. In general, routing protocols define how routers communicate with each other for the purpose of sharing and updating routing information. More specifically, a routing protocol is an implementation of a routing algorithm that uses metrics to discover a path or paths to a particular destination within a network. In IPv4, you had RIP. It's a basic distance vector routing protocol. There's two versions of RIP. The first is version 1, defined in RFC 1058. It's written as RIPv1. The second is version 2, defined by RFC 2453, and it's written as RIPv2. Among all the other features in RIPv2, it added support for variable length subnets. I want you to note that RIP communications are UDP-based. So RIP-based routers send and receive datagrams on UDP port 520. So we've talked about OSPF for Open Shortest Path First. It's defined in RFC 2328, and it's the premier link state routing protocol used on TCP/IP networks. Now, when we use the term open, we're referring to the non-proprietary nature of the protocol. OSPF routing is based on configurable values, also called metrics, that may be based on network bandwidth, delay, or even monetary cost. Sometimes when we talk cost, we're talking money, but we're also talking path and time and number of networks. By default, the metric should be for route determination, and it's based on network bandwidth. And the next slide is going to show you the basic architecture of OSPF. If you're not familiar with Dijkstra's algorithm from a data and algorithms course, search that. It's pretty simple to understand, but it's some of the main algorithmic logic used in the architecture. So there's seven, not two. There's a few basic types of LSAs. You have your router link advertisement, network link, network summary. Remember, there's 6 that are listed. Type 6 is not. So when you're studying these, correlate your types to the names. And here is a diagram of the OSPF hello, LSA, and the link state update process. And here is the header structure for OSPF. So we've talked about interior and exterior routing protocols. So the interior gateway routing protocol, the IGRP, was developed in the 80s by Cisco and was updated in the early 90s to the enhanced IGRP. These protocols integrate the capability of link state routing along with the distance vector routing protocol. We've also talked about BGP. These are exterior gateway protocols, and exterior gateway protocols are used to exchange routing information between separate autonomous systems. So these protocols are referred to as inter-domain routing protocols. It's interesting, the name exterior gateway protocol was assigned to the first implementation of this type of routing. EGP is defined in RFC 904, and the border gateway protocol replaces EGP routing. So there's 3 types of routing operations: inter-autonomous system routing, intra-autonomous, and pass-through autonomous system routing. And when configured for intra-autonomous system routing, BGP routers are located within the same AS. In pass-through autonomous system routing, it allows the BGP peer routers to exchange routing information across an AS that does not support BGP. Here is a diagram of a typical BGP design. So in IPv6, the routing protocols are largely extensions of their IPv4 counterparts. In general, IPv6 routing protocols can be organized into interior gateway protocols, or IGPs, exterior gateway protocols, or EGPs, distance vector-based, link state-based, and so on and so forth. The autonomous system, ASs, and the autonomous system number, ASN, a set of networks that are controlled by a single administrative entity, route both IPv4 and IPv6 traffic. RIPNG for IPv6 is based on the protocols and the algorithm currently being used by IPv4, covered by RFC 2080, which is the proposed standard for RIPNG for IPv6, and it represents a minimum change to the RIPv2 protocol. OSPF for IPv6, or OSPF v3, is based on v2, with various enhancements added, and it runs directly on IPv6 and distributes IPv6 prefixes. EIGRP for IPv6, it's changed little for IPv6. It's essentially the same protocol and still uses the best of distance vector and link state. And here's an RIPNG packet format diagram. And here is an OSPF v3 header format. So intermediate system to intermediate system, so ISIS for IPv6. It's an intra-domain, routing information exchange protocol, and it's ISIS is an extendable intra-domain routing protocol specified in RFC 1195 that allows each router within the routing domain to send a link state protocol data unit containing information about the router. MP-BGP, defined in RFC 4760, allows MGP4 to contain information about other protocols such as MPLS, IPX, L through VPN, and IPv6. For IPv6 networks to support BGP4 or to support routing and other network layer protocols, BGP4 needs two additions. One, the ability to associate the IPv6 protocol with the next hop information, and also the ability to associate the IPv6 protocol with NLRI. So managing routing on an in-house Internetwork, IP routing protocols have a shortcoming. They do not discriminate between users, types of traffic, and so on. They know only how to get to a network, and policy-based routing addresses this shortcoming. Simply configuring an IGP on an in-house network will likely establish connectivity between each subnet. However, there's much more to managing routing than simply establishing connectivity. An administrator should consider policy first and foremost. IP routing protocols have a shortcoming. Again, they don't discriminate between users and types of traffic. When we talk in this section that the administrator should keep a map of the network, you really should. An interesting example of network mapping takes place as part of the Cisco Network Academy's third semester. When you're studying for your CCNA, you have to take part in a practical project called a threaded case study. And many of these students, their work is published on the internet if you do a search, and you're going to get tons of results. Some of the network documentation and diagrams they created are very well done. And you should learn about it, because this is something you should do on network design projects. So routing on and off a wide area network, you need to consider many factors when you choose a routing protocol for your enterprise. So we're going to talk about some of the various network models and appropriate routing protocols. So if you have several small offices, if the network in question is relatively small, perhaps a dozen locations or less, where each has its own subnet and an internet connection, consider using no routing protocol. Wherever possible, the simplest solution is best. If a routing protocol is required, then RIP is probably the simplest solution. When you're connecting a server that supports routing, that way the server can dynamically choose the best path. And the routers that do not support any other protocols are employed. When we talk about hub and spoke, many corporations have a central office with many satellites or branches. Usually all branch offices connect directly to the hub, where enterprise systems like ERP packages, a mainframe, and servers reside. The distinguishing feature on this network is that the router in the hub needs to know how to get to many sites, but the routers at the branch offices only have a single connection out of the office, or perhaps only two, when a slow backup link is used to provide redundancy over a fast primary link. If there's only one connection, or only one connection is used at any one time, it does not, you don't want to use bandwidth advertising all routes to each spoke, not to mention router processor and memory resources. So for routers on the ends of the spokes, all you need is a single default route that points to the hub. In this situation, on-demand routing, or ODR, is a good choice. Frame relay and ATM use virtual circuits, so one physical interface can actually be logically partitioned into several logical interfaces. So multi-protocol, Cisco's EIGRP protocol can support the routing of both IPv4 and IPv6 traffic at the same time. So it can conserve a lot of resources in some cases, but it does require that you only use Cisco equipment. For mobile users, some of the most difficult types of networks to implement and manage is one where the users are always moving around, from laptop, tablet, and smartphone users to telecommuters and companies that frequently rearrange their workspaces to accommodate changes in personnel. It's clear that new trends are emerging that TCP/IP was really not built to handle. But fortunately, in the last few years, we had a maturation of technologies that support a mobile workforce. So, data-enabled cellular devices, 802.11 wireless, from A to N and AX and everywhere in between. Broadband wireless technologies, dial-up and broadband for home-based connections. But how does this normally work? Well, mostly with DHCP. So mobile IP is defined by the IETF in RFCs 2003 through 2006 and 3220, which takes over for 2002. It essentially allows an IP host to travel anywhere there's a mobile IP agent, so a router configured with the protocol, and it still maintains its home IP address. So now you have the LAM, so local area mobility. It's a Cisco proprietary feature, operates by using the routing table. When a router is configured with LAM, it watches for traffic on the LAN that does not match its own IP address. And when it finds the traffic, it installs an ARP entry in the cache and a host route, a route entry with 32-bit subnet mask in its routing table. So routing to and from the internet, BGP4 is the exterior routing protocol in use on the internet, at least at the time of the book. BGP probably doesn't deserve its arcane reputation. It requires a major hardware investment if it's to be deployed properly. Fortunately, only a few companies have networks complex enough to require BGP, and as a general rule, only networks that connect to multiple internet providers should even use BGP. So, even so, no discussion of routing would be complete without covering this protocol, because it's part and parcel of the internet backbone. So when you think about securing routers and routing behavior, the two aspects of routing services that you have to secure are the routers and the routing protocols. Routers contain network addressing information. They're a doorway between networks. The doorways need to be guarded closely. So in terms of securing routers, turn off services you don't need, shut down any ports you're not using, configure strong access to prevent tampering, and secure physical access. In terms of routing protocols, OSPF supports several forms of authentication, including MD5, though you really shouldn't be using MD5. IPv1 has no security. So, in summary, we talked about data link protocols. So again, manages transfer of datagrams across the network. At the data link layer, protocols must deliver services like delimitation, bit level integrity checks, addressing, and protocol identification. Ethernet 2 frames are the most common type of frames in LAN, and understanding your frame layouts is crucial for the proper handling of contents. It's important to understand the differences in field layouts and meanings when comparing various frame types for any particular network medium. And it's imperative to understand how TCP/IP manages the translation between MAC and numeric IP addresses. Understanding ARP packet fields illuminates the address resolution process. Proxy ARP permits the router to interconnect multiple network segments. Remember, reverse ARP is the reverse of ARP too. Network layer protocols make their way into the data link layer through a process known as data encapsulation. When a frame has to travel from one network segment to another, a process to resolve its route must occur. So, important characteristics of IP datagrams: time to live, fragmentation of frames, service delivery. Routing protocols and routers, they provide a mechanism that can forward traffic from a sender subnet to the receiver subnet. Routers, depending on the various routing protocols, manage the packet forwarding process. The distance vector routing protocols, so RIP, are a crude metric of routing costs. OSPF supports a more sophisticated routing structure that breaks up a network into specific areas. Routing characteristics help determine what kind of routing protocols to use in specific applications. And managing routing on a complex network involves understanding how and when to use exterior and interior routing protocols. Router tables define the topology between and behavior of IP networks, and it's essential to manage your router security and updates as safely as possible. IPv6 routing mechanisms are the same as their IPv4 counterparts in terms of functionality. IPv6, you have multicast listener discovery, which specifies multicast behaviors as well as the MLD packets and messaging types. And finally, IPv6 routing protocols are RIPNG, OSPF VC, V3, EIGRP for IPv6, ISIS for IPv6, and MPBGP. Thanks for sticking around for the long video. Hopefully this at least was a good summary of your chapter. Again, if you have any questions, let me know. Thanks.